In this video, I'm going to do two problems for 8.2, which is confidence intervals for sample means with the t-score instead of a z-score. This first video I'm going to do by hand, just using a calculator and writing out the problems. And the second example, I will use Google Sheets to calculate the confidence interval. And I believe Google Sheets is the easiest way to do, to do these calculations, but you can find what works for you and what you're most comfortable with. Remember, the t-score is used when either we have less than 30 sampled in our survey, so n is 30 or less, or if we do not know the population standard deviation, and so we need to calculate the standard deviation of our sample and rely on that sample standard deviation instead of the population standard deviation. So for this first problem, it says 108 Americans were surveyed to determine the number of hours they spend watching television each month. It was revealed that they watched an average of 151 hours each month with a standard deviation of 32 hours. Remember, this standard deviation of 32 hours is of that sampling. Part A asks us to identify the following. So first, X bar, that was given to us. It was 151 hours. This next one is asking for the population standard deviation. Sigma shows the population standard deviation. We don't actually know the population standard deviation. We only know the sample standard deviation. So we're going to change this to equal S, which is the notation for the sample standard deviation. And that is 32 hours. Finally, N is 108. Part D says to define the random variable X in words. The random variable X is used to notate one single value in our survey. So it would be one American and the number of hours that they watch TV each month. The random variable X bar is the sample mean or the point estimate. So the average number of hours per month that the 108 Americans each watch. Part D is asking us which distribution, T or Z, which should we use for this problem and why? We are going to use T distribution and find a t-score for this, because even though there are 108 Americans in the survey, so that's over 30, we are not given a population standard deviation, so we are relying on this standard deviation here, which is the sample standard deviation. Finally, part E, or almost finally, tells us to calculate and construct a 99% confidence interval for the population mean. Hours spent watching television per month. So remember, the formula for calculating a confidence interval for t-score is X bar plus or minus T times S, which is the sample standard deviation, divided by the square root of N. All of this is equal to the error-bound margin. So first we can calculate that error-bound margin, which we need to know T, S, and N. T we could find on the chart, but unfortunately that chart only gives up to 30 and then gives 100 and 1,000. So it's not a very helpful one because it won't tell us this 108 that's in the problem. But I calculated T using Google Sheets. The formula, remember the T inverse function of 0.01, because it's asking for a 99% confidence interval. So there's 1% of the values are in those two tails. So 0.01, comma, degrees of freedom is equal to n minus 1. So 108 minus 1 is equal to 107, which using Google Sheets is equal to 2.6 approximately. So that's our t-score. So error bound margin 2.6 times 32 divided by the square root of 108. You can pause the video to calculate that, or I'll just cut the suspense and let you know that that is equal to 8.07. So that means that our confidence interval is equal to x bar, which is 151 plus or minus 8.07. So our 99% confidence interval is equal to 142.93, which is 151 subtract 8.07, and 159.807, or 0.8. 0.07. Sorry, I'm looking at my notes and had that written down wrong. 0.07. That means that we are 99% confident that the true population mean hours spent watching television is between 142.9 and 159 hours. Finally, part F asks us, why would the margin of error change if the confidence interval were lowered to 95%? This should actually say, how would the margin of error change? And if we lowered the confidence level to 95%, we're less certain of our estimation. That means we can have a smaller margin of error and a smaller confidence interval. All right. Example 2, we are actually going to use Google Sheets for the entire process. I think that's a great way to keep your data organized and to have Google Sheets do all of the math for you, so you're not having to continually type different things into your calculator. You can just click on the cells and have Google Sheets take care of most of the process. Example 2 says HCP is working to understand the scope of industrial pollution in the human body. Industrial chemicals may enter the body through pollution or as ingredients in consumer products. In October 2018, the scientists at HTP tested blood samples for 20 newborn infants for 430 industrial chemicals. The following table shows how many chemicals were found in those samples. And so here's our data, and the problem is asking us to construct a 90% confidence interval for the mean number of industrial chemicals in a newborn's blood. We only have 20 different newborns blood samples, but we want to project to know the average number that we could expect any given newborn would have in their blood. So if you open up a Google Sheets document, the first thing you're going to want to do is plug in all of this data into Google Sheets. I've already typed these values in. This is obviously not the most sexy process, but sometimes you just need to plug and chug and enter some data. A lot of jobs these days are actually people just typing numbers into some type of data set. So it's not the most fun thing to do, but it's necessary. All right, so once we have our 20 data values, then we can start calculating some of the things that we need in order to calculate the confidence interval. If you remember, here is the formula for the confidence interval with a t-score. we'll be using a t-score because there's not a population standard deviation known, and it is also only 20 samples, so not, which is less than the 30 required to meet the standard for a z-score. But going back to this formula, x bar plus or minus t times sample standard deviation divided by the square root of n, which is the number of samples in our survey. So the first thing that we want to know is x bar, which is just the average of our sample. And we've already highlighted all of those. And we can find our average number of chemicals in each newborn's blood in the sample is 127.45. The next thing that we want to know is our t-score. So remember that formula we could do this with the chart, but it's obviously, while we have Google Sheets open, it's easy to have Google Sheets do the entire process for us, and that would be T inverse T distribution, or T inv. And then the first thing you need to type in is, since this is a 90% confidence interval, that means that there's 10% probability that the data point would fall in either one of those two tails at the ends of the normal distribution graph. So 0.1, comma, and then the degrees of freedom in this would be, if n is 20, degrees of freedom is n minus 1, so 19. And that gives us a t-score of 1.73 approximately. Next, we want to know the sample standard deviation. Again, Google Sheets can do that for us. Standard deviation of a sample, this is the .s instead of .p, which is the entire population. We only have a sampling of data, so we'll use that one. And again, highlight A1 through A20, which represents all of our data. We can see that the sample standard deviation is approximately 25.97. And finally, n is equal to 20. Now, with this formula, that for a confidence interval, it's always of a sample mean is x bar plus or minus all of this, which is the margin of error, or the error-bound margin. So if we calculate that next, error-bound margin is equal to our t-score times our sample standard deviation times the square root of n. That gives us a, oops, I was going to say 200 seems like a awfully large sample stand. 200 seems like an awful large error-bound margin, so I realized that I multiplied by the square root instead of divided by the square root. So here we go. It's actually t times sample standard deviation divided by the square root of n gives us an error-bound margin of 10.04. Now, if we want to find the lower limit of our confidence interval, be equal to x bar subtract the error-bound margin. So the lower limit of the confidence interval is 117, and the upper limit is equal to x bar add error-bound margin 137.49. So our 90% confidence interval is 117.41, 137.49. And that means that 90% of the time the true population mean will be within this range.